Hello and good evening, everyone. Welcome to the channel of IEEE Student Branch Chapter of Netaji Subhash Engineering College. My name is Farooq Aziz and I am from Computer Intelligence Society and the Department of Electronics and Communication Engineering second year. I would like to warmly welcome you all to a series talk on the theme of evolutionary computing and covering the core concepts and major algorithms on this field. This event is organized by IEEE Computer Intelligence Society (SBC) of Netaji Engineering College. We are privileged to have Dr. Sujay Saha, Assistant Professor of HIT, as our esteemed speaker for the first day talk of this series today. His primary research interests include computational biology, machine learning, and brain computing interface. So, without further ado, let's welcome our guest. Hello, sir.
Hello, good evening. Good evening, Farooq. Thank you for your introduction. Good evening, everyone. Myself, Dr. Sujay Saha from Heritage Institute of Technology. So may I start, Farooq?
The screen is all yours, sir.
Yeah, good evening. So without much delay, let me start. So before that, let me share my screen first. I hope the slides are visible. So I am asked to give a presentation on a gentle introduction to evolutionary computing with genetic algorithms. Now, it's not a topic that can be finished within a 1 hour or so. But as I am asked that to make it a presentation for which is suitable for the students, so that's why I make it a very make it a very introductory level so that everyone can understand the basic theories, basic principles of evolutionary computing as well as the genetic algorithms. Now, I thank the organizers to give me the opportunity to give this presentation in front of you. Okay, so let me start. Now, before every such tools, I always want to mention that who is the inventor of any technique. Okay, so like this, the evolutionary computing it was first introduced in the 1960s by the person whose name is I. Reichenbach. Now, many persons, many researchers, they actually use this evolutionary computing in different ways. Okay, there are different ways of explaining or representing the term called evolutionary computing or evolutionary algorithms. Now, the difference, I hope you can understand that evolutionary algorithms means computing means that the algorithms can be implemented. Okay, so that's why it is called the evolutionary computing. Now, one theory that some of the researchers they term that evolutionary algorithms as a population-based optimization techniques. So two terms are there. One is called that one is the population-based, and another one is the optimization technique. So let us first let me first discuss about this population-based. So population-based means that it starts with a collection of solutions, the set of solutions, and over time that population will be evolved. And where to evolve? It evolved to a better solution in every iteration, in every generation. Okay. So basically it is a population, and you know what is a population. Population means that the collection of individuals, right? A set of individuals. So that is a population. And second term is the optimization technique. So optimization, you know that the problems can be of generally two types: decision type problems and optimization problems. In optimization problems, there will be some function, objective function, that needs to be optimized. So basically we are trying to find out the better solutions. We are trying to find out uh, what is called as a optimal solutions, if not optimum. Okay, I hope you understand between that optimal and optimum solutions. So that population will be evolved towards the better solutions every time. So that is the one theory regarding these evolutionary algorithms. Second one is that soft computing approaches. Now many of you, I hope you understand about this soft computing approaches. Soft computing means that it is actually different from the hard computing, where hard computing is looking for the exact solutions, right? Exact solutions. But there are some problems which are normally called as the NP complete problems. So for those, it is very difficult to find out the exact solutions in polynomial time, and we don't have uh, such algorithms that can find the good solutions in polynomial time, and we don't even know that whether it is possible to find out in future or not. So that's why for those problems, the alternative way is the soft computing approaches. Soft computing approaches, what it does, that it finds a good solutions, a satisfiable solutions in reasonably good amount of time, right? So evolutionary computing is also termed as a soft computing approaches. These are the subset of soft computing approaches, because there are a lot of other soft computing approaches available. So evolutionary algorithms are one of them. And the third way of looking for this evolutionary algorithm is the meta heuristic algorithms. It is also termed as meta heuristic. Now you can ask me the question that what is the difference, why not it is heuristic. Now you know, heuristic is actually the difference between meta heuristic and heuristic. Heuristic is problem dependent, whereas meta heuristic is problem independent. As for example, if you I'm sure if you have studied artificial intelligence, if you have not, there is not an issue. There is an algorithm named as A star. Okay, I hope those who have studied artificial intelligence, they have heard about this algorithm. It's a very popular algorithm, A star. Now in A star, there is a concept of the heuristic, right? So A star, if I apply A star for a 8 puzzle problem, for a problem like 8 puzzle problem, the well-known heuristic that will be applied for that is a Manhattan distance, right? So basically what I'm trying to say, try to understand that this is problem specific. This Manhattan distance, it is used as an heuristic for a 8 puzzle problem. It is specific to that problem. So heuristic is actually the problem dependent, but meta heuristic is a general concept, is a general framework. It is not dependent on a particular problem. So evolutionary algorithm is actually a meta heuristic algorithm. So whenever you are going to use this technique or tool to a particular problem, you need to map according to that domain, right? So that's why it is a meta heuristic. So there are a lot of other terminologies which are associated with evolutionary algorithm, but these are the fundamental things. That's why I have chosen these three. So one is the population based meta heuristic, and it is also a subset of the soft computing approaches. Okay, so whatever the properties of a soft computing approaches are, evolutionary algorithms follow those. Okay. Now, I hope the slides. You can see the slides. Uh, some of the participants says that the slides are not changing. I am not. I don't know. Uh, okay, let me stop once again and then I again share it. I don't know why it is not changing. Can you see the slides now? Can anyone please respond? No, can you see this slide, evolutionary algorithm? I am at this moment, yeah, third slide, right. So now see, can you see the fourth slide now? Fine, okay. So let me, I am not going to the slide, uh, uh, what it's called that, I am not going in the slideshow mode. I am changing the slides in this way, okay. I think it is okay with you. Okay, fine, thank you. Okay, so what I am saying that actually I told you, if you guys not don't see this slide, I just explained this one a little bit ago, that it's a population based optimization techniques, soft computing approaches, and meta heuristic algorithms. These are the things that I have already explained. Okay, so now I am coming to the evolutionary algorithm. So as I have already mentioned that evolutionary algorithms refers to an algorithm that evolves a problem solution over many iterations, and those iterations are called generation in terms of the biological foundation. Okay, so basically one iteration is said to be the one generation, and it is evolved through generation to generation, right? So from one generation we are moving to the next generation, from that generation we are moving to the next generation, and in this way it will go on. Okay, and every time my objective is that we are going from the better solutions, we are going to the better solutions, or we are going from one better solution to another, the much better solutions. Okay, because the reason is that we are actually applying these algorithms to solve the optimization problems, right? And optimization problems, as I already mentioned, that there is a function that needs to be optimized. Okay, and the basic fundamental or basic principle of evolutionary algorithm that you probably know, I will come to that later in detail, that the survival of the fittest and the natural genetics or natural selection, right? So let me explain that thing in this picture, with this picture. I hope you can see this slide. I hope you can see this slide. So this is the pictorial representation of any evolutionary algorithms. It is actually explain you the basic principle. So what I am saying, that as I have mentioned, that it starts from the population. It starts from the initial population. So as I have already mentioned, that population is nothing but a collection of individuals. So these are the individuals. Okay, so how many individuals you have taken? 3 3 6 2. So 8 individuals are there. Each round is an individual. Okay, and these are, I am telling you, these are the possible candidate solution. So actually, when we start with a initial set of solutions, right? Now this is actually different from the hill climbing approach. I don't know how many of you have heard about the hill climbing. Hill climbing is actually, the difference is that there is only one solution. It consider one solution at a time, and it try to achieve the better solution in the next iteration, right? But here in evolutionary algorithms, we are talking about, or we are considering a population. Now population means a set of solutions. Okay, now we don't know that whether these are the best solutions or not. That is our evolutionary algorithms will check, that will find that from this whether we can move to the better solutions or not, right? So the question that comes, that how do you know that whether this solution or this solution or this individual, whether they are the to evaluate them? And how to evaluate them? For them there is a fitness function. So the fitness function, I will come to later on, that about the examples of the fitness functions. So fitness function will be applied on every individual to evaluate them and got the fitness values. So fitness value actually gives you the idea that how fit an individual is in this what I can say, in this environment, right? So that is the fitness. So after applying those fitness values, you got the fitness function. After applying those fitness function, you got the fitness values, right? That is called the evaluation. Now after you have done this evaluation, now your job is to select. As I said, that the basic principle is survival of the fittest. So the individual will be survived if they are fit enough. Now you see, among these 8 individuals, 3 will be cut. 3 are cut. So 3 are cut means those are discarded. Why those are discarded? Because they are not fit enough to move to the next generation, right? So that is called the selection. Now after this selection, now you got this one. Now you can ask me the question, sir, we discard these 3 out of 8, then how can the next one can again be contain the 8 individuals? The reason is the population size. The size of the population should be fixed, right? So if I start with the 8 individuals, so here also we should have the 8 individuals, right? So how do you get, because 3 will be discarded, 3 are discarded. So for that you have to create a clone, right? Maybe there are different strategies are there. One of the strategies is that which one is the best. You find that which one is the best. So take or create some more copies of the best individual, right? So what is the reason? The reason is, obvious reason is that we are looking for the best. We are looking for the best solution. We are looking for the better solutions. So always we try to go for the best. So that is the reason why we are creating the clone or copies, multiple copies of the best individual. So we got this one, okay, and with this, those are actually going for the reproduction, right? So since it is based on the principle of the natural genetics. So natural genetics, the features which are there, the operators which are there, those will be applied over here. I will coming to that. So so with this, you got the individuals in the next generation, and the same cycle will be repeating. Same cycle will be repeating up to a certain number of iterations, whatever you want. That is actually depend on the user. If the user wants that I want to make it 1,000 times run, so it will run on 1,000 times. Okay, so that is the basic fundamental ideas of evolutionary algorithms, right? Is this clear? Is this picture clear? Okay, so if so, now I am moving to the genetic algorithm now. So okay, so before that I just give you this show you this slide. Now various evolutionary algorithm techniques are there. Among them, two are significant. One is that genetic algorithms, another one is genetic programming. Now you might be confused, or you might be surprised to see that maybe you have heard about these two terms, and you have you assume that these two are same, but not. Okay, so there is a difference between the genetic algorithm and genetic programming. Now since I am here to explain genetic algorithms, so I just ignore that genetic programming at this moment. Okay, now, so genetic algorithm, as it is written over here, that it is the search and optimization algorithms based on Darwin's natural selection and natural genetics. Okay, so natural selection and natural genetics, that is the fundamental principle on which the genetic algorithms are built on. Okay, and it's a searching technique, right? It's a search. So, but there is a difference between the genetic algorithm search and the normal search. Now, what is the difference? I am just coming to that. Now, see what is written over here, that if we are solving some problem, we are usually looking for some solutions which will be the best among the others. The space of all feasible solutions is called a search space. So basically, search space is the set of, or the collection of all the solutions, and among them the desired solution is also there. Okay, but the search space is a very huge space, and if I go for the classical search, if I am moving to the class using the classical search or sequential search, it is very difficult to find out the desired one. So that's why we are taking the genetic algorithm. Genetic algorithm is what is the advantage? Advantage is that it's a random search. Okay, so it's a random search. So basically, from one point, it jumps to another point. Again, from that point, it jumps to another point. Right. So it's a randomly it searches the search space, and for a huge search space, this is the ideal one, because if you go for the sequential one, then the problem that you can face is the picture that I have shown over here, and I am sure that some of you can identify that what is the problem that I try to mean over here. In the left hand side, if the search space is like this, then your classical search will be good enough, right? Because it's a one best solution, and when you are reaching at the peak, you find that all the solutions surrounding to this one are inferior, right? So you got the solution. But if your search space is like this, now what is this plot trying to say? It's trying to say that it is a possibility that we can stuck at the local optima. Okay, we can stuck at the local optima. What is the meaning? The meaning is that if we are at the peak of this one, the left hand side, the smaller one, then at this point, my assumption is that no other solution is better than this, right? But the better solution, the best solution is somewhere else. But we are starting over here. So if I starting over here, then your search algorithm, your classical search algorithm will return this one as the best solution. but it is a wrong. Okay, ultimately you are getting a wrong solution. So genetic algorithm can try or can make you to get rid of that. There is a way that by which you can come out from this local optimum, right? So that's why genetic algorithm. So that's why for a search space which is like this, it is a better approach. Genetic algorithm is a better approach. Like say hill climbing. Hill climbing has also the same problem. I hope those who are already aware of that hill climbing is actually facing the same problem, that's stucking at the local optimum. Okay, so for that, if you are using some random search, then there is a way to come out from that. Okay, so genetic algorithm, as it is written, that it's a search which can be used to solve the optimization problems, right? I hope it is okay. Okay, so now let's move on. Now, as I have already said about the evolutionary algorithms, who have introduced that. Similarly, for genetic algorithms, Professor John Holland, he is a person who actually, what I can say, that he introduced the term genetic algorithm, but Professor Goldberg, okay, Professor Goldberg, who actually made that genetic algorithm popular. Okay, if anyone is interested in genetic algorithm, you can find his book, the very famous book of Goldberg, genetic algorithm, right? It's a very well written. If you are interested, you can go through that. Okay, now fine. So as I have already mentioned, that the principle of natural selection, that is the two principles of genetic algorithm. One is the natural selection, another one is the natural genetics. The rule of thumb is that select the best and discard the best. Okay, so you always try to select the best, and which is the worst, you just discard it, because those are not fit enough to move to the next generation, to go to the next generation, right? So that's why the simple principle is select the best and discard the rest. But whenever you are trying to apply genetic algorithm on some particular problem, first of all, the first step is that you have to map your algorithm to that problem domain, right? And that is called the encoding. I will come to that. I will come to that later on, that what are the different ways of doing the encoding. So encoding is the first step. That is actually the representing the solutions, right? Now, as I have said, that these are the solutions, right? These are the solutions. These are the individuals, but you have to represent those individuals in a suitable way, right? So that is called the encoding. And second one is the fitness function. Now, fitness function is also be different from one problem to another problem, right? Like say, as I have written over here, that for graph coloring problem, I hope many of you are familiar with the graph coloring problem. So graph coloring problem, the fitness function will be the chromatic number. Suppose if you want to apply genetic algorithm on graph coloring problem, your fitness function could be the chromatic number. Now, chromatic number is what? Chromatic number is the number of colors that is required to color that graph, right? So that will be a minimization function. You have to minimize it, right? So that is the fitness function for a graph coloring problem. Similarly, if you are using that, solving the traveling salesman problem, or maybe the knapsack problem, your fitness function will be different, right? So encoding as well as fitness function, that will be on the basis of the problem that you are going to solve. Okay, so the first step is that is the encoding, how to represent. Okay, and next thing is that natural genetics. So natural genetics, you know that the basic unit which actually represents the characteristics of individuals, those are called genes, right? And the collection of the genes for any living organisms there is a set of chromosomes, right? So in this right hand side, if you see that this is a chromosome, and the individual, the basic unit of that chromosome is the gene, right? Now those are also called as alleles, right? Because this is the value, right, of that gene. Suppose this gene which is pointed by this arrow, this gene represents the color of the eyes of human being, right? So this gene, the value, on the basis of that value, the color of the eyes could be different from one person to another person, right? So gene actually carries the characteristics, right? For a natural genetics, so gene is very, very much significant. Okay. And second one is that the features or the operators or the operations which are what I can say, which are used over here, those are the reproduction. Because reproduction, what is that? That genes from the parents combine to form a whole new chromosome. Basically, the offsprings, the children are generated from the parents, and characteristics and the offsprings or the children will carry the characteristics, some of the traits of their parents, right? So that is the principle of the natural genetics, right? Due to by this reproduction or recombination, which is actually termed as crossover in terms of genetic algorithm domain. So by this, the offsprings or the children will carry some of the traits of their parents. Okay, so the basic in any living organisms, the chromosomes are the strings, right? Chromosomes are nothing but the strings which contain the genes. Okay, and what is gene? Now gene is the basic unit which actually store or represent the characteristics of a particular characteristic. Okay, so that much you need to know. Okay, it is not like that to apply or to work on genetic algorithm you have to know lot of biological things. Not like that. Okay, only the simple biological concept will be enough. Okay, now from this I just give you the idea that how the genetic algorithm works over here. So see, so this is suppose the generation N which contains these individuals. So basically now see, now we are moving from the physical phenomenon to the genetic algorithm domain, right? So whenever we are moving to the genetic algorithm domain, our individuals is actually represented as a chromosome. So this is one individual. So you see, if I want to similarize these things, so these are the individuals, right? So these individuals is now represented by these chromosomes, by these strings. Okay, chromosomes, you just forget about chromosomes, you just think about that those are nothing but the strings, right? How to represent those strings, that is the question of the encoding, right? When I will show you the encoding, you can see the picture, right? But for this time being, you just see that these are the strings, the individuals are represented by the strings. Okay, and on those strings some operators are going on, some operators are applied, and we will get the strings in the next generation. That is the fundamental thing, right? So from nth generation we are moving to the n+1 generation, right? So basically this is the population in the nth generation, this is the population in the n+1st generation, right? Now this is the flowchart. This is the flowchart of a simple genetic algorithm. I hope whatever I have already told you, you can get the idea that very simple and straightforward way. And a genetic algorithm, why it is popular? One of the reasons is that it is very easy to implement. Okay, if someone wants to write a C program, it is very easy to implement a genetic algorithm, because the steps are straightforward. So what it does, so initialize the population. So initialize the population is, suppose this is the population, so you just initialize the strings, right? Now there is a condition checking that whether I have made the terminating condition or not. Okay, now if it is so, then I will stop. Now if it is not, then I will move to that, evaluate the solution. So I hope by this time you got the idea that what is the meaning of evaluate the solutions. So evaluate the solution means that to apply that fitness functions, you got the fitness values. Now there are three basic operators. I will come to that one by one. Three basic operators: selection, crossover, mutation. Now selection is always going to occur, but crossover and mutation, there is no guarantee that in every iteration that both crossover and mutation will take place, right? So I will show you why it is so. So crossover, mutation, through this operator, it goes on to the next step. Again, it goes on here, check whether it made the terminating condition or not. If it is not, again this cycle is going on. Now if it is so, then you evaluate the solutions and return the best one at that point, right? Now as I have already mentioned earlier, that genetic algorithm, there is no guarantee, since it is a meta heuristic, there is no guarantee that every time you will get the optimum solution. But the point is that there is a guarantee that you will get a good solution in reasonably good amount of time. That is the fundamental point over the significance of genetic algorithm. Are you getting? Okay, fine. So now let's move on. Now encoding. So as I have already mentioned, that this is the first step, right? Encoding. So encoding, by encoding, what I'm trying to say, that it's a mapping between the phenotype space to the genotype space. Now what is the basic difference? Phenotype is the physical characteristic, right? Suppose, as I have already mentioned, that the color of eyes of some person is black, or the color of the hair of some person is brown, right? That is the phenotype feature. That is called the phenotype representation. But whenever you are dealing with a genetic algorithm, you have to map it in a genotype space, right? Suppose this gene represents the color of the hair, okay? And suppose the possible values are brown and black. So maybe 1 represents the black and 0 represents brown. So this is called the genotype space. This is called the genotype representation. And that is the difference. So whenever you are doing the encoding, encoding means actually the mapping between the phenotype space to genotype space, right? Now I am going to the encoding, different type of encodings. Now it can be binary encoding, it can be permutation encoding, it can be real valued encoding. Now it depends on which problem you are dealing with, right? It is not necessary that every time we have to use the binary encoding, not like that. Okay, maybe say for the graph coloring problem, if I want to apply genetic algorithm on graph coloring problem, binary encoding will not be the ideal way or ideal encoding technique, right? We can use the integer encoding, right? Maybe if I want to represent the weights of an artificial neural network, then in that case the weight can be the real values. So in that case, the real value encoding will be the ideal choice, right? So that depends on that. For a particular problem, the problem in your hand, for that problem, which one will be the suitable? Whether it is a binary encoding is suitable, whether it is a permutation encoding. For a traveling salesman problem, this permutation encoding is the ideal one, right? So that is called the encoding. As I have already mentioned, what is encoding? That it's a mapping Now, whenever you got this one, basically it's a representation, it's a genotype representation of some physical phenomenon, right? Now after doing this encoding, next one is the genetic operators, right? As I have already shown you in the flow chart. So encoding, initialize the population means basically you have done the encoding, right? Now before going to the operators, next one is the evaluation. Evaluation means the fitness function. Actually, I maybe missed one thing. Fitness function. So fitness function, as I have already mentioned, that fitness is actually gives you the idea that how fit a particular individual is, or how fit a particular solution is, right? Suppose for a graph coloring problem, you got one solution, but you don't know whether that solution, how better or how good a solution is, right? So how do you know how good a solution is? By getting the chromatic number, right, of that solution. So chromatic number is the fitness function for that particular problem, right? So fitness function, and it is actually different from one problem to another problem. It is problem dependent fitness function, right? It is not like that I have used a function and that function it can be applied to all the problems. Not like that. Okay, so fitness function is a problem dependent, right? It's a problem dependent, and its objective is to know that how fit a particular solution is, how good a particular solution is, whether that solution is fit enough to go to the next generation or not. Getting? Okay. So after this, the three operators: selection, crossover, mutation. Now, selection is always going to happen. Selection means that from that initial population, you have to select the best, right? So that they can go for the reproduction, right? Basically, in other words, I can say that to create the mating pool, right? To create the mating pool, right? So selection refers to choosing the parents for recombination. That is the fundamental idea for the selection, right? But there are some techniques for selection. Now, it is not possible for me to discuss all the techniques over here, but I am choosing here for the first one, and which is the most what I can say, the most popular one, that is a Rowlett wheel selection. Okay, so let me go through the Rowlett wheel selection first. So Rowlett wheel selection, what is said, that the main idea is the fitter is the solution with the most chances to be chosen. Okay, and the chances are proportional to their fitness. So what is the meaning? The meaning is that the chances of selecting a solution depends on the fitness of that particular solution. So fitter is the solution, the more chances are there to select in the next generation. That is the Rowlett wheel selection. Okay, now why it is called Rowlett wheel? What is the significance? So let me discuss that thing. So here in this table, you see that there are 4 solutions I have taken. The strings, 4 strings are there. Correspondingly, the fitness values are given. Okay, so that is the total fitness and percentage of total. Percentage of total means that is basically the percentage of this string with respect to the total fitness. So it is basically 169 by 1170 into 100. That is the percentage. Now see, among these 4, the second one is the highest fitness, has the highest fitness, right? Then after that, the fourth one, then the first one, and the third one is the worst. Third one is the worst, right? Now, what this Rowlett wheel selection is done. When it's a abstract idea. Now, what is done? That you just think about a wheel. You just think about a wheel, a imaginary wheel, and the wheel, the area is divided into different regions as per the fitness of the individuals. Okay, so what I'm saying, that there are 4 strings. So this wheel, you see, this wheel is divided into 4 regions: 1, 2, 3, 4, right? Purple, blue, green, and maybe off white. Okay, on the basis of the fitness value of the particular strings, right? So this is for the chromosome 2, this is for the chromosome 1, this is for the chromosome 4, and this is for the chromosome 3, right? So chromosome 3 is the fitness as the lowest, so that's why it got the less portion of the wheel. Okay, now what you have to do, you just spin the ball, spin the wheel, right? There will be a marker over here, somewhere around here. There will be a marker. Now, when the wheel come to a stop, it stops. The area which that marker marks points to, that will be selected, right? So, as I have already mentioned, that roulette wheel is an abstract idea. When you are going to implement it, there should not be any wheel like that. There should not be any wheel concept over there. But it's an abstract idea that is going to be applied. Okay, that is going to be implemented. Okay, so the idea is that the portion covered, the string which covers the major portion of the wheel, there is a chance of getting the selected frequently, or the chances are high, right? So this is the concept of the roulette wheel selection. Okay, now there is a drawback. Can anyone tell me that what is the drawback of this technique? Now the drawback is, I hope you can see, you can point it out, you can find that it will not going to work, or it will not a ideal selection technique when either all the strings have the fitness value very close to each other. That is one scenario. And number 2, if one string contains the 99%, I am just saying in a very vague way, the 99% of the wheel. Okay, so that means if one string, in one situation, one string is a major portion of the wheel, it is consuming, then the reason is that every time that string will be selected, right? If I select the strings on the basis of the fitness value, okay, that is the one case, that is the one extreme case. And another case is if all the strings fitness values are very close enough, close to each other, then also roulette wheel is not going to perform well as the expected. It is not giving you the desired result. It is not giving you the expected result. Okay. So for that, we have another technique which is called as rank selection. Now, rank selection is what? That here the population or the individuals are selected on the basis of their rank, not their fitness values. Okay, so what I'm trying to say, you just see this picture. This is the scenario that I am talking about, that all these, say there are 6 strings, and you see the fitness values very close to each other. Okay, so that's why they are taking almost the same areas of the wheel, consumes the almost same areas of the wheel, right? So that's why what is the alternative? The alternative is that you first create a rank. Okay, on the basis of the fitness, you create the rank. Okay, first rank, second rank, third rank, fourth, fifth, sixth. So these are the ranks. Now select the strings on the basis of their ranks, not on the basis of their fitness. Right? So this is the rank selection will be ideal for this type of scenarios. Right? But as I have already mentioned, that Rowlett wheel selection is the most popular one. The scenarios that I am mentioning, those scenarios are not very frequent to occur. Those are not frequently occurred. So that's why Rowlett wheel selection will be the most popular one. Is the most popular one as far as the genetic algorithm is concerned. Okay. Now apart from that, there are another selection that is called the tournament selection. Now I am just skipping this part over here because it's not possible to explain all these things in this short period of time. You can find it in any other sources, because if you get the idea that why selection is required, then I think there will not be any difficulty to understand the other techniques, right? Now there is another technique that I have written over here, that is steady state selection. Now this is not any particular method. This is actually applicable for all the techniques of selection. Now what is saying over here, that offspring of the individual selected from each generation go back into the pre-existing gene pool, replacing some of the less fit numbers. Some individuals are retained between generations. So what is saying over here, say here for this case, so this third one will be discarded because it is the worst, right? As far as the genetic algorithm is concerned, select the best, discard the rest. So this one is the worst, so I have to discard it. So if I have to discard it, then 1, 2 and 4 will be in the mating pool. There is no doubt about that. Now what will be the fourth one? Because as I have already mentioned, the size of the population should remain fixed. So if I start with the 4 size population size 4, I have to make it 4 every time, right? So for that, what I will do, I will make the 2 copies. If I can make the 2 copies of the best one, then I will get the size of the population 4, right? So that is actually called the steady state. So every time you have to consider that steady state selection, because that you have to keep the size of the population fixed. Okay, fine. So now move on to the crossover. So selection is done. So I am creating the mating pool. Now the next step is the crossover. So crossover, what it does, it combines the genetic material of 2 parent chromosomes and produce a new child possessing the characteristics of both the parents. As I have already mentioned, that it is a phenomena of the natural genetics, that the children carries some of the properties of their parents. Okay, and I have already also mentioned that it is not necessary that crossover or mutation, it is likely to be happen in every generation. Not like that, because there is a probabilistic scenario. There is a crossover probability, right? Typically the ranges are from 0.6 to 0.9. So crossover probability is always higher than the mutation probability. That is a convention. That is a convention, right? Why I am coming to that? So crossover probability. So if I run my program 10 times, and if the crossover probability is 0.9, then out of 10, 9 times the crossover will occur. So there can be one case when the crossover will not going to take place. Okay, so how the crossover will work? So let me show you. So suppose it will be better if I can present this slide, then you can see, because there is an animation over here. But okay, now the thing is, a random point is chosen on the individual chromosomes and the genetic material is exchanged at this point. So suppose I am choosing these 2 parents to be crossed. Okay, and another thing that I have to choose, that is the crossover point, and that is also at the random. That point is also going to be selected on a random basis. Okay, now if it is so, if this is the crossover site, this is the crossover point, Now, this part of the parent 1 will be merged with this part of parent 2. I hope you can see the mouse pointer on the slide. So then you can understand. So this part of the parent 1 will be merged with this part of parent 2 and make it a offspring 1. And similarly, this part of parent 2 will be combined with this part of the parent 1 to get the offspring 2. Right? So this is called a single point crossover because the crossover site is 1. Right? There can be variations. There can be variations like this 2-point crossover. Now you see what is happening. Chromosome 1, chromosome 2. So 2-point crossover. So there are 2 crossover sites. There are 2 crossover points. Okay. Now how this offspring 1 has been generated? You see very carefully that 1 say this one. So 11011 that will be clubbed with the middle part of the chromosome 2, and again it will be clubbed with the third part of the chromosome 1, right? So 11011, then 11000, and then 11010. So that is one offspring. And the second offspring is this part will be clubbed with this part and this part. So this is offspring 1. Okay. So in this way, you can increase the crossover points. It can be 3-point crossover. It can be n-point crossovers. Okay. But the idea is that by crossover, you exchange the genetic properties or the materials of the parents. Okay. So this material and this material, the genetic material of these chromosomes, these 2 chromosomes, 2 parents are exchanged to generate the offspring. Okay. So basically new solutions. Actually, this is the idea of creating the new solutions. Okay. As I have already said that it's a huge search space. So in that search space, you are obviously this, although these are newly generated, but those should be belong to somewhere else in the search space. Right? So that is not discovered. That is not discovered yet. So your algorithm will discover it. Okay. So that's why it is a random process. It's a randomized algorithm. Right? There is another crossover techniques that is called the uniform crossover. There is no exchange of the materials. That is a slight difference. What is that? Now we don't divide the chromosome into segments. Rather, we treat each gene separately. Assign heads to one parent, tails to another. Basically, suppose these are the 2 parent chromosomes. You flip a coin. You flip a coin for each gene. Suppose you are saying that head is for the first parent and tail is for the second parent, right? So if it is head, then you just flip those things, right? Similarly for the second gene, similarly for the third gene, similarly for the fourth gene. In this way, you cross. So that is called the uniform crossover, right? That is another crossover technique. Now, apart from crossover, there is a mutation. Now, mutation, I mentioned in the very beginning that there is a chance of stacking at the local optimum, if you remember, right? And I have already also mentioned at that time that genetic algorithm has the way to come out from that local optima, right? So mutation is the one of the techniques, one technique, one way of going to that. Okay, so mutation is used. So that's why normally the mutation probability is very, very less compared to the crossover probability. So mutation is not going to happen very frequently. Why it is so? Because this is the why mutation is required. Mutation is required. Suppose for a last couple of iterations, you find that solutions does not change, right? Solution does not change. So what is happened? You two conclusions you can make, that either I am reaching at the solution, I am finding the solution, or maybe I can stuck at the local optimum. So if the second thought is true, so what I will do, I will do the mutation. So what is the mutation? Mutation is basically the changes, the random changes to some particular bit. Random changes, right? Maybe this bit is changed, this bit is changed, this one is changed, this one is changed, and so on. Okay, and after doing this mutation, I am going to the same job again, and let me see whether I am getting the better solutions or not. If still I am not getting the better solution, then I will stop, but I will try for that. So that is a mutation. Okay, so mutation is basically the random changes. Okay, not for all the strings, maybe 2 or 3. I am just selecting randomly. Okay, I am selecting randomly that suppose second one, they say 101, or maybe say 50th one, I am doing the changes. Okay, and try it once and see whether I am getting the better solutions or not. Okay, now so already actually I am since it is a 1 hour presentation, so I am crossing that thing. So but I want to show you one example, because without example so far whatever I told you is a theoretical thing. So let me show you 1 or 2 examples that how genetic algorithm can be applied to a particular problem, right? So suppose this is a very simple problem you are giving, that there is a function called x square that you have to maximize, and in the range from 0 to 31. Okay, and you are asked to apply genetic algorithm to solve that problem, right? Now what are the things that is given? That binary encoding, population size is 4, 1 point crossover, bitwise mutation, Rowlett wheel selection, and random initialization. So these are the assumptions that I have made before I'm going to apply the algorithm, right? So now let me show you. Now you see, so since the size of the population is 4, so excuse me for a minute. Sorry. So size of the population is 4. So I am taking 4 strings, right? Now you can ask me the question that, sir, how do you get this initial solution? It's a random thing. Okay, it's a written over here that random initialization. So randomly I am starting with this 4. Okay. Now x's value. So x value is what? These are the decimal values of these binary strings, and these are the fitness values, right? What is the fitness value? Because your objective function is fx equal to x square, right? So you just do the x square over here, you got the fitness values. The probability is what I have already shown you. Probability is this divided by this. The fitness value of a ith individual divided by the total fitness. That is the probability. Okay, because it's a Rowlett wheel selection. So for a Rowlett wheel selection, the probability of selecting the individual will be on the basis of the fitness. Okay, and there is another feature which is called expected count. Now expected count is actually giving you the idea that how many copies you need to make in the next generation in the mating pool. Okay, and how do you get this expected count? It is actually the multiplied. You just multiply the probability with 4. Why 4? 4 is the size of the population. If the size of the population is 5, then you need to multiply it by 5. Okay, so 4 into 0.14, 0.14, that is 0.58. 4 into 0.49, 1.97, 0.22, 1.23. Now you see, if you just round it off, if you just round it off, then it will give you 1. This one is 2. This one is 0, and this one is again 1. So what does it mean? You take 1 copy of the first one, 2 copies of the second one, 0 copy of the third one, and 4th copy of the 1 copy of the 4th one, right? and it is actually as per your algorithm, right? Because it's a worst. Third one is the worst, so you cannot take this any copies of this one, so that is 0, right? So now you see how the mating pool has been created. Now see, one copy of the first string, so 0 1 1 0 1 0 1 1 0 1, one copy. Two copies of the second one, 1 1 0 0 0 1 1 0 0 0 1 1 0 0 0, and one copy of the fourth one, 1 0 0 1 1, right? Is that okay? I hope. Now here I am taking the crossover sites. Here I am taking the crossover sites. Okay, so crossover sites 4 4 2 2. I am taking 4 4 2 2 4 4 2 2. Okay, so now the crossover has been taken place. 0 1 1 0 0 1 1 0 0 1 1 1 0 0 1. Here 1 1 0 1 1 and 1 0 0 0 0. Right? And again the same thing. The cycle will be continued. X value, then fitness, then again that of here this is the offspring 0 1 1 0 0. So here, and then I am doing some mutation over here, and just for the example purpose I am just showing you that mutation. Here the 0, this bit has been changed to 1, and here this bit has been changed to 1, and again I am doing the same thing. Okay, and you see that I am actually, by this mutation I am actually improving. Why? Now see, here the excess values are 12 25 27 16. Now you see the excess values are 26 25 27 80. So I am actually moving to that, because your objective function is fx equal to x square maximize. You have to maximize it, so you are moving to the better solutions. Okay, you got it? Now see, so this is actually a very simple example. Okay, now I am showing you another example which is a bit difficult. Why it is a difficult? From this function you can understand why it is a difficult one. Now first of all, it is a 2-parameter function. That is a one thing. Second one is there is a range of the variables given. Okay, x1 is ranging from minus 3 to 12.1, and x2 is from 4.1 to 5.8. Okay, now see how can you approach or take this approach to apply genetic algorithm. Now first of all, I'm just going to the example over here. So first of all, you have to find out the required bits. Okay, for a variable, how many bits are required? How many bits are required? Because say there are two variables, x1 and x2. So how many bits are required to represent x1, and how many bits are required to represent x2? Okay, the formula is, what is the formula? The formula is, first of all, you have to find out this bj minus aj. What is bj aj? This is the domain, this is the range. So for x1 my range is minus 3 to 12.1, and here it is 4.1 to 5.8. Okay, now you see, so what is done? bj minus aj. So bj minus aj, 12.1 minus of minus 3 into 10 to the power 5. Okay, and then you see that in which range this value belongs to. So it is from greater than 2 to the power 17 to less than equal to 2 to the power 18. So x1, the number of bits that is required is 18 bits. Okay, similarly for x2, the number of bits that is required is 15 bits. Okay, so total the length of the string, the length of the chromosome will be 33 bits, where the first 18 bits will be for x1 and the rest will be for x2. Are you getting? Okay, so since the ranges are there, since the range of the variable is given, so by this you can find out the number of bits required. Okay, now after that you have to find out the decimal values of those. So that is a very not very difficult one, that for every string you can get the decimal values, corresponding decimal values by this formula. Okay, so with this I got the initial population. Suppose size of the population is 10, so I am getting the 10 strings like this randomly. Okay, so with the decimal values of those strings like this. Okay, so as I have already mentioned that first 18 bits will be for x1 and next 15 bits will be for x2. Okay, now the evaluation. So evaluation is very easy because you have the function. What is that function? Fx equal to this. So evaluation you can do. So you can get the evaluation for every string, and you find that v3 is the worst one and v4 is the highest one. Okay, so this is the weakest one and this is the strongest one. Okay, now I am going to apply the Rowlett wheel. Now see, this is actually the implementation technique of Rowlett wheel. How can I do this? So calculate the total fitness. I can calculate the total fitness. Then calculate the selection probability. Selection probability is what? Selection probability is the fitness of every individual divided by the total fitness. Okay, and then calculate the cumulative probability. Okay, so let me show you the example over here. So this is the total probability. Okay, total probability. Next is the individual probability of the 10 strings, and then cumulative probability. Cumulative probability is what? So P1 will be P1, sorry, Q1 will be P1, Q2 will be P1 plus P2, Q3 will be P1 plus P2 plus P3, Q4 will be P1 plus P2 plus P3 plus P4, and in this way it is gone. Now, how do you implement the Rowlett wheel? Now the idea is generate a random number R from the range 0 to 1. So these are the random number, right? Now the formula says that if R is less than equal to Q1, that means if the first one is less than equal to Q1, then Q1 will be selected. If not, then select the kth chromosome if qk minus 1 less than or less than equal to qk. So what does it mean? Suppose your first random number is this, right? So now you check that in which interval this random number falls. Okay, so this number is actually in between q3 and q4, right? So q4 will be selected. Okay, similarly this one is again fall between this one and this one, so q4 is again selected. This one is in the range between q7 and q8, so q8 will be selected. So in this way you see v4, two copies of v4, then v8, v9. So this is the mating pool that will be selected by the Rowlett wheel selection, right? And then the usual crossover, mutation, whatever you can apply. After doing, you got this next generation strings, and with this next generation you do the same process again and again. Okay, so that's the basic ideas. So that's where I will stop. So these are the two books that I refer. One is that I have already mentioned, that book of the Goldberg. That is a very standard books for genetic algorithm. If anyone is interested, you can follow it. And I have taken this book also. I have referred this one also. So these are the references. And so thank you very much. So this is where I end. So if anyone having any question, I can take.
Thank you, sir. It was a great lecture. It seems, sir, we currently don't have any questions. Maybe.
Yeah, right now I can't see any question in the chat window, in the comment section.
Yes, sir.
If anyone wants to communicate offline, you can ask me questions. I have given my email ID. So if anyone interested, you can talk to me later.
So that's been from sir. If you have any other questions, as I said, please feel free to connect with him on LinkedIn or reach out him through his email ID. Aditya has already dropped those, I guess. If not, please Aditya provide the LinkedIn and email IDs. And before we end, make sure you subscribe to our YouTube channel if you haven't yet, and follow us on our social handles. The link to our Facebook and LinkedIn pages will be provided in the comment section below. And apart from this, we're bringing forth to you a feedback form. This form will be active till the next hour. Please go ahead and fill it. This would be a great help to us. Well, this marks the end of today's session. So on behalf of everyone, I would like to thank Dr. Sujay Saha again for taking time and being here today. It was a great learning experience. And for everyone else, thank you for supporting us by joining in. As these are the trying times, I I only can hope that our viewers learn more and follow all the safety protocols necessary. Thank you.
Thank you very much.